All right. One thing I want to do today is this is a result that's developed in the textbook, and I'm just going to use it for one example problem. And it's the magnetic field on the axis of a current loop. And this is another example of using your right hand for something. We're looking at a circular loop of wire here. And let's just imagine that the current in the wire is going in this direction from our viewpoint. And it's another way that you use your right hand. And that is that if you curl your direction, your fingers in the direction that the current is flowing, your thumb will point in the direction that the magnetic field happens to be. And maybe it'll work better if we just imagine, okay, the current is in this plane here. And if I curl my fingers in that direction, the magnetic field on the axis of the loop is going to be in this direction. Turns out this a single loop of current will produce a dipole-shaped field, and it's very hard to deal with that off-axis. In fact, you have to use an infinite series to be able to calculate the field. They're called Legendre polynomials, but on the axis, it's not too bad. And as far as the geometry is concerned, if we let A be the radius of the loop, and then we imagine that we go out a distance x on the axis away from the center of the loop, then the magnetic field strength out there, and it's just in the x direction if you're on this thing, will equal mu naught times I times a squared divided by 2 times x squared plus the quantity x squared plus a squared to the 3/2. So that's just what it happens to be. If x is 0, that would put you at the center of the loop. So, and they derive this. I do not expect you to memorize this formula, but it is possible to derive this using the Biot-Savart law, and which I don't know if I named it out loud last week. That's the one that looks like this. So it's not Biot-Savart, it's Biot-Savart, or I think your book calls it the law of Biot and Savart. But anyway, at the center of the loop, x is equal to 0, and you just set x equal to 0 down here, and you have a squared to the 3/2, which is just a, I think, isn't it? Wait a second. A squared to the 3/2. No, it's a cubed. Okay, it ends up being this. You'd end up with bx equals mu naught I over 2a. Although check that to be sure. If this is 0, I'd have a squared to the 3/2. That's a cubed on the bottom and a squared on top. Yeah, should be that. So anyway, that's the way it works. So if the current goes in that direction, the field goes in that direction. If the current is clockwise, let's see. So this would be a field coming out of the page. If the field, or if the current is clockwise like this, the field would be into the page. So yet another use of the right hand, and we'll run into at least one more in this unit on magnetism. So let's put that to work here. And we have a circular loop of radius r, capital R this time, and which isn't a, and it carries a current I2 in a clockwise direction. The center of the loop is a distance d above a long straight wire. What are the magnitude and direction of the current I1? That's a current that's down here. Can't read it very well. This is I1 in this wire, and we haven't figured out what direction it's going yet. If the magnetic field at the center of the loop is zero. Okay, well, first of all, I2 is the current going around here. It's going in a clockwise direction. That will make the magnetic field here into the page if we were only considering this current right here. And that magnetic field strength is going to be, this is the magnetic field of the loop, just the loop, is going to be mu naught times I over 2A. Whoops, it's not A in this case, it's 2 capital R. So that's what we'll have to have there. Anyway, that's it. And it's into the page. Well, we're going to have a current I1 that is exactly opposite that thing. So it's going to have to be out of the page. Well, if the current in I1 is going that way, kind of another right-hand rule here, the magnetic field of that will be into the page. So we have to have I1 going to the right to make a magnetic field out of the page. So that's something that we know. And what is the current of a loop of wire? So B wire is going to be, actually, we could kind of use Ampere's law for this, which we're going to be hitting today. But it'll be, oh, this is I2 up here. Yeah, mu naught I over 2 pi d is the magnetic field of a wire. Usually we call it an R down here, but in this case we'll be at distance A or distance d away from the thing. And somehow this one has to equal in magnitude mu naught I2 over 2 capital R. So basically, we just have to solve for I1 in this case. Now, this may seem kind of baffling, but we did a result last week where if you have a wire into the, or a current going into the page, that the magnetic field of that current, poke your thumb in the direction of the current flow, and the magnetic field is out here looking like that. And if this is the distance R, then we ended up with B was equal to, and that's a current I, B was equal to mu naught I over 2 pi R. That's the magnetic field strength. And it's concentric circles around the wire. Okay, so we're just trying to make the magnetic field at the very center of this loop be zero. So we set these two things equal to each other. And let's see, we've got mu naught on each side. We have a 2 on each side, and we'll get that I1 has to equal, let's see, I2, well, pi times d times I2 divided by capital R. So kind of a weird expression, but it's just an example of using this little thing. Okay, our next unit or topic in here, I don't plan on spending a whole lot of time about magnetic fields on current loops, not much more than I just did, or that's probably enough. Anyway, it's just a formula that's developed in the textbook. It's good practice using the Biot-Savart law and cross products to derive it for yourself. But I remember when I was studying for the physics GRE, it's the graduate record exam. I practiced doing that, and then there wasn't anything related to it on the test. So, but that's okay. No scholarly effort is ever wasted. Okay, another topic for today, though, is something called Ampere's law. And it's kind of mysterious, like Gauss's law is. If you remember Gauss's law, we stated it fairly simply for electricity, at least. For magnetism, Gauss's law is equal to 0, but it's the integral of E dot dA was equal to, actually, usually we start off with the flux of the electric field through a closed surface is equal to that, and it's equal to the charge enclosed by the surface divided by epsilon naught. So that was Gauss's law. And this depends on something from multivariable calculus called the divergence theorem. And the divergence theorem is one of the very last units in the textbook when you're studying multivariable calculus. And a lot of times by the time you get there, it's just sort of over the top. Okay, well, there's something else from multivariable calculus called Stokes's theorem or Stokes' theorem. And that's what Ampere's law ends up depending on. And this is what Ampere's law looks like. It's got another symbol that looks like this, but this time it isn't over a closed surface. It's over a closed loop. And it just looks like this, B dot dl. Okay. Now, we did a line integral with the electric field, which was, if you remember that the change in potential between 2 points was the negative of the integral of the electric field along a line. And that's just equal to the change in potential between 2 points. And if we were to do an integral of E dot dl around a closed loop, we'd end up with 0 for the result because we'd be right back at the same point that we started with. But with the magnetic field, that's not the case. Turns out that a magnetic field is not a conservative field. And what it ends up equaling is mu naught times the current that is enclosed, ENCL, that's enclosed by the loop you just did. So this is kind of weird. Again, why in the world should this be the case? Well, take multivariable calculus. When you get to the Stokes theorem part, and I'm not even positive it's in the book all the time, I'm going to go grab a multivariable calculus book, just a sec. This is a book that was just in a stack that people were giving away one time. Fundamental theorems of vector calculus. There's Green's theorem. Let's see. Stokes theorem. Okay, yeah, it's the second to last thing in the book in multivariable calculus. So, and I wonder if they even mention Ampere's law in here. Oh, they do. Okay. Yeah. So that's good. And then the last section in this book is the divergence theorem until you get to the appendixes, like the language of mathematics and stuff like that. Anyway, So it is in a multivariable calculus book, but it's at the tail end of the book. But that's what this depends on. So here's the idea. If you have, let's suppose you've got a current I1 that's into the page right here. And by the way, this integral can be done over any arbitrary shape. So if you take and integrate b dot dl over this weird shape around here, in this case, it would end up equaling mu naught times I1. Now, if you happen to have another current that's coming out of the page, so that could be I2, then this weird integral where we're going around in this direction like that, if you're going in a counterclockwise direction, any current that's into the page would be considered positive, but any current that's coming out of the page would be considered negative, and don't worry about that. B dot dl, okay, it would actually equal mu naught times I1 minus I2. And so you can do it for any number of these things, and this weird integral ends up equaling that. Well, what use could that possibly be? Here's the use. If you ever happen to forget that the magnetic field of a long straight wire is whatever it happens to be, we just used it on a problem here, you can use Ampere's law to figure that out. Because let me show you. Remember, okay, that's the field on the loop of a wire, so ignore that for now. But let's just suppose we have a current I that's into the page here, and we'll draw a circle that goes around that thing. And in this case, I'm going to make it a nice perfect circle, except I'm getting hung up on something on the paper here, under the paper. Yeah. Huh, what is down there? I don't know. Anyway, I'll just finish this off by hand. So this is a circle of radius r here. Now I happen to remember that if you've got a long straight current, the magnetic field forms concentric circles around that thing, and that's where the magnetic field is constant. So I'll do this. The integral of b dot dl, okay, and I'll let with my b pointing in that direction, I'm just going to integrate around the circle. That way b is always in the same direction as dl. I know that b is constant, so this will end up equaling b dl. Remember, this is the scalar product, so when you do this, it's gives you a scalar, and b is constant, so it can come outside the integral. And so I'll have b times the integral around the circle of dl, and integrating dl around a circle gives you 2 times pi times the radius of the circle. So I'll get b times 2 pi r. So there's my integral, and that'll equal mu naught times the current, or the current that's enclosed by the circle, which is just I. So that reminds me that the magnetic field of a long straight wire is mu naught I over 2 pi r. So quick way of getting that, instead of doing the integral of the Biot-Savart law from minus infinity to infinity of, oh, let's see, dl cross r hat over r squared and da 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 da. So that's the way you can do it. But you can also use this for some other geometries. And let me show you one of them. Oh man, I can't draw this. Suppose you had a long coil of wire. Okay, and let's suppose that the current in the wire is, and we just imagine looking at a slice of this long coil of wire. So we could think of kind of cutting it in half here and having a whole bunch of loops like that. And on this side, let's just imagine that the current is always going into the page. And I should put the X's in the center of those things. And down here, the current's always coming out of the page. And these coils are evenly spaced. We've got lots of symmetry, and let's just imagine that they continue on in this direction and in this direction for a long ways. Okay, and we'd like to know what's going to be the magnetic field down the axis or in the center of this loop of current here. Okay, well, what we do is we make this artificial surface here. And by the way, this long coil of wire like this is called a solenoid. And the solenoid in your car, I think cars still have solenoids. Haven't had to monkey with one in a long time, but I don't work on cars much anymore because they're all too much electronics. But it's something that when you have your car in the start position, it would make current go through a solenoid, which is a long coil of wire here. It would exert a force on a metallic rod that was inside the solenoid and pull it in one direction. And on one end of that rod would be a toothed gear that would match up with the flywheel on your car. And then the starter motor actually spins that thing and makes it turn your engine over. And if you're simultaneously giving it gasoline and making the sparks go, then your car starts. There used to be ways to bypass some of this stuff. I remember my father-in-law had a huge Oldsmobile at one time, and went out to dinner with them, and their car wouldn't start, and so he had me crawl underneath and short out the contacts on something with a screwdriver, and then the solenoid would engage and start the car. It was quite fun. Not. Anyway, it's a solenoid. So you make this artificial surf line here. This is going to be our path that we take for the integral of b dot dl. And we're going to integrate that along here. Well, you've got all these loops. They're going to be making a magnetic field that points in this direction inside that thing. And so that's where we'll get it. And if you're outside of this thing, you're going to get some magnetic fields in one direction from these wires that are coming up, and then the opposite direction from this. And because they spread to an infinite direction in either thing, there's no magnetic field outside the solenoid, is kind of the hand wavy argument. And the only place you get it inside of here is the only place you get contributions to this integral is only when you're going in the same direction or opposite the direction of the magnetic field in there. So let's make our integral go in this direction. You get no contribution here, no contribution here, no contribution here, and along here we'll get a contribution that's just going to equal b times whatever this length is. So let's call this length. Okay. And this ends up becoming integral, whoops, now it's just the integral along this one part of b dl. You expect b to be constant there, and so you pull that out. So it's going to be b times the integral of dl over a length L, which is just going to be b times L. And that will equal mu naught times however many wires you happen to have contained in your thing here. Well, the number of wires you're going to have is going to equal some number n. Let's just call it lowercase n. So mu naught n times I, and that's how much stuff is contained in there. Well, the magnetic field then that's in there will actually equal mu naught n I over L, and n over L ends up being the number of turns per unit length, and I may have screwed up by using a lowercase n for that. Maybe I'll use a capital N for the number of things that we actually got, and define lowercase n to be the number of turns per unit length on the coil. And then you can say that the magnetic field of that solenoid is just mu naught n times I. So that'll be the number of turns per unit length. Okay, and I know that was hand wavy. They do a better job of presenting that in the textbook than I just did. So, but that is how you can use Ampere's law to find out the magnetic field of a solenoid. And the one other place where you use Ampere's law to get the magnetic field of something is for a toroid, which is a circular coil of wire. And look in the book to see a picture of a toroid, because I can't draw them worth beans. So anyway, so let's use Ampere's law for a few problems here. And I think tomorrow we might have another couple, or maybe, well, maybe not tomorrow, maybe in class when in person. But anyway, we have a cylindrical conductor of radius R equals 2.5 centimeters, carries a current of 2.5 amps along its length. Okay, that's not a lot of current for a wire that has a radius of 2.5 centimeters, because if it's got a radius of 2.5 centimeters, its diameter is 5 centimeters. That's a really fat wire. And yeah, I don't know. Maybe there's some place they use wires that thick. About the thickest wires I ever saw were in Japan. We took the bullet train from Kyoto to Tokyo, and I'm guessing they had wires running along over the tops of the track that ran the train, and I'm thinking they might have been either 15 millimeters, maybe a centimeter and a half in diameter, maybe up to 2 centimeters, something like that. But that's what the train ran on. And these things are going like almost 200 miles an hour. So they must take a lot of current, but a wire that thick was fine for delivering that. So this one's a little bit unbelievable, maybe, but let's just suppose that the magnetic field of this thing, or not the magnetic field, but the electric current is going into the page, and it's a capital R for the radius of it. And it says the current is uniformly distributed throughout the cross section of the conductor. So something that you might define is the current density for this problem. And in this case, it'll equal the total amount of current, the 2.5 amps, divided by pi times R squared. And if you happen to include the let's see. Well, if you have some area, this is current per unit area. So if you pick any little area within this wire and multiplied whatever this area happened to be by I over pi r squared, that'd give you how much current there is flowing into that little tiny area. And the reason I'm doing that is because we're going to calculate the magnetic field midway along the radius of the wire. That's at r over 2. So if this thing has current going in this direction, even within the wire, there's going to be magnetic fields there. So we can figure out what that happens to be. So let's do this. We'll have I'm going to use Ampere's law, the integral of B dot dl. Okay, well, I'm going to use for my Amperian loop in this case, just a circle that's centered on that thing. Imagine that. I could probably try to draw this better. I think I will. There's the center of it. Maybe this is the outside of it. It's actually bigger than 2.5 centimeters, and this is going to be the inside surface. So this will be r over 2, and this thing's going to be capital R. Okay. And my Amperian loop, integral of B dot dl, with current going into the thing, it'll end up being the integral of B dl, which is going to equal B times the integral of dl. And for part A, my radius is going to be r over 2, and so the circumference there is going to be 2 times pi times the radius. So this will equal B times 2 times pi times r over 2. This is a path length now around a circle of radius r over 2, and that'll equal mu naught times the amount of current that I've got enclosed in this thing. Well, how much current will that be? Okay, and if I multiply this out, I get B times pi times capital R. And that'll equal mu naught. Well, what's the area of this thing? It's going to be pi times r over 2 squared. That's the area of a circle. And if I multiply that by my current density, oh, this should have been capital R squared. Okay, so here's mu naught. Here's the area of the circle I'm including, and I'm multiplying that by the current density. And so what do I get? B times pi times R. Let's see. The pi's divide out. I've got 1/4 R squared and R squared on the bottom. So I'll have mu naught times 1/4 I is what I happen to have. Through this circle that's just half the radius, I only have 1/4 of the total current, and 3/4 of the total current is the rest of it. So anyway, the magnetic field there is going to be, let's see, mu naught times I divided by 4 pi capital R. So that's what it would happen to be. And then find the distance below the surface of the conductor at which the magnitude of the magnetic field has the same value as the magnetic field at R over 2. this is kind of interesting, actually. Um, that's halfway along the wire. As you go closer and closer, actually, what would the magnetic field be at the surface of this thing? It'd be 2 times pi times r. So it's weaker when you're underneath here. So it's increasing as you go out. And I guess, I don't know, but be outside the wire, and this will be part B. Outside, B is going to equal mu naught I over 2 times pi times r. And this is for r greater than capital R, is when that happens to work. Well, somewhere out there, this will actually equal mu naught I over 4 times pi times capital R. Well, let's see, the mu naught i's go away. Oh, I'm trying to solve for r here. So little r, I flip both of these. I can say 2 times pi times little r over mu naught I will equal 4 times pi times capital R over mu naught I. Simple fraction equals simple fraction. Their reciprocals are equal. And I can cross out things that are common to both sides, like pi's and that. And I get that little r ends up being 4 halves capital R, which is 2 capital R. So that's where that magnetic field outside the wire will be the same strength as it is at R over 2 inside. So that was kind of an interesting problem. Okay, next one here. Okay, here's a solenoid. It's a closely wound long solenoid of overall length 30 centimeters. So it's this long. That's 30 centimeters. Has a magnetic field of magnitude 5 times 10 to the minus 4th Tesla at its center due to a current of 1 amp. How many turns of wire are on the solenoid? Well, hmm. I've got an expression here for, oh, I know what happened. I just did that problem where I figured out the magnetic field on a solenoid, or for an example, and now I put the page down and lost it. Do I have to redo it? Where did I draw that? Back of this, back of that. Here it is. There we go. Mu naught times n times I. Okay, that's not so bad. So, and they give me an expression or a value for the magnetic field near the center. Give me that. I know what mu naught is. And so how many turns of wire are on the solenoid? Okay. Well, I can solve what I've got here for n, and little n will equal the number of turns on the solenoid divided by the length of the solenoid, which is 30 centimeters or 0.30 meters. We've only got one sig fig everywhere on here. So let's see how this turns out. In this case, little n will equal the magnetic field divided by mu naught times I. And so actually the capital N will end up equaling B times L divided by mu naught I. Now, I would expect this thing's going to come out dimensionless because this is just a number of turns. Okay, and there aren't really any units to that. You do one turn, you do two turns, and so forth. So let's see what happens here. My magnetic field strength, 5 times 10 to the minus fourth Tesla, but a Tesla is a Newton per amp meter. And then I've got the length of this thing, which is 0.3 meters. So the meters will go away and I'll have newtons per amp. And then let's see, mu naught, 4 pi times 10 to the minus 7th. Then I just forgot the units on that. Yeah. It's Monday. I haven't had to think all weekend. Uh, oh no. I know we had better units than this. In the back of the book, they've got it as Webers per amp meter. Okay, need to back up a ways in here. Okay, it was in chapter 28 at the start that we introduced mu naught. Oh, Tesla meters per amp. Okay. Oh, should have just called this a Tesla then. Okay, so Tesla meters. Hey, let's see. Oh, and I'm multiplying by a current of 1 amps. Yay, units divide out. Well, that was a lot of work. Yeah, so we can just plug this in here and see how many turns we've got. And we'll have to probably, this will probably be an integer, but who knows how many we'll have here. And I get about roughly 120 for the number of turns. And that's supposedly we would only have one significant figure, but we'll just go with that. Anyway, I had to use, I don't know, magnetic field of a solenoid, or that's the number of turns per unit length. Then this one wasn't too bad, actually. Okay, let's do one more that's maybe a little more interesting here. Some superconducting alloys. A superconductor is a material that has zero resistance to electric current flow under certain conditions. And the certain conditions would be a lot of superconductors have to be kept at very low temperatures. And if they go above that, then they cease to be superconductors. Also, they'll usually have limits to the amount of current that they can carry, although it's usually expressed as a limit to the current density that they can carry. But anyway, for example, I don't know what you call this kind of wire. NB is niobium, SN is whatever, selenium or something, I don't know. But at 10K, that's 10 Kelvin, so kind of cold, but they can carry 1,000 amps and maintain its superconductivity. Determine the maximum B field which can be achieved in a solenoid of length 25 centimeters if 1,000 turns of that wire are wrapped around the outside surface. Well, the turns per unit length would be 1,000 turns, which you can assume that that is an exact number. It's an integer. So over 0.25 meters, that's what 25 centimeters happens to equal. So that'd be, we've only got not much in the way of significant figures. Anyway, 4 times 10 to the third turns per meter, and the actual units on those turns per meters are just meters to the -1. So that's what we have there. Let's see, maximum B field. Well, B is just going to be mu naught times N times I. It's a solenoid, and that's the magnetic field of a solenoid. So we would have 4 pi times 10 to the -7th. And now I forgot what the units on that were. Tesla meters per amp. Okay. Times 4 times 10 to the third. And if I write that as 1 over meters, that may help. And then the current it can carry is 10 to the third amps. So the magnetic field strength, oh, let's see. Or 5 times 10 to the -7th times and I get about 5 Tesla. Let's see, the meters divide out, the amps divide out, and I'm left with Tesla. So 5 Tesla, that's pretty strong. By the way, if you go to some place that has an MRI machine, magnetic resonance imaging is what that stands for, they'll have magnetic fields of comparable strengths to this. And I don't know, I think they might have superconductors, so they have to cool those things down with liquid helium to get them, to keep them cold enough so that they're superconducting. So a practical application of that stuff. MRI stands for this. And originally, it was called NMR, for nuclear magnetic resonance. And when they started using it for a medical diagnostic technique, people didn't like the nuclear in the name, so they changed it to MRI. But it's the same thing. They have a magnetic field that oscillates at a particular frequency, and some of the nuclei in your body, I think it's in the hydrogen atoms, respond to that frequency, and so they can map out stuff in your body pretty well with those. Okay, I think I'll stop there for today, and maybe tomorrow when we meet live, we can do some more Ampere's law things. This is something that seems pretty mysterious just because of the origin and multivariable calculus, but I've got some conceptual exercises that we could work on to try to improve your understanding of that as well. And then tomorrow we'll do another electronics lab on, I think, capacitors tomorrow. We're going to do some experiments to look at how putting charge on a capacitor takes time, and we can use that to figure out by looking at how the current through something varies with time, we can use that to determine the capacitance of a capacitor by its behavior in a circuit. So we'll stop recording here, and I'll see you tomorrow. Tomorrow, I have some paperwork I'll have you fill out